All right, so we get to talk about perception now, which is I don't know if you know this, but that's like my original thing was all perception. Then I started to get into the other side, so this will be pretty fun. Um, okay, so for this module, which is really short, there's actually only two small lectures in this. What basically we're going to do is we're going to talk about categorical perception, and then we're going to move on into theories of speech perception. And this time we're looking at categorical perception. What is categorical perception? A really good example of this that's, visually striking is colors. You can see here that we know that the color spectrum is in nanometers, right? It's in nanometers of electromagnetic radiation from the sun. It's continuous. We've got all these different colors that we can perceive. We know that they hit the eye. All the different wavelengths hit the eye, and they interact with the rhodopsins in our eye in different ways. It's okay. It's fine if you don't know anything about that. It's totally cool. What you do, all you need to understand is we see a continuum of colors, right? Just a bunch of different colors of a range are coming into our eye at any given time. But what we perceive is not a continuous spectrum of color. It's actually like a block of hues. So you can look at this, and I can say, like, right over to the left, right here, this is like, here's pink, sort of. It's not really pink. It's kind of like purpley, right? It's like light. There's probably a word for it that I'm not coming up with. This also is a really good time for me to tell you something that might break your brain, and it's kind of cool, is that some shades of purple don't actually exist. You see that they're not on this spectrum. They're over here, sort of, but also they're over here. What it is that some things that look purple to us have these colors and these colors, and then it's purple. So on the actual spectrum, we don't have a color that corresponds to purple, but we can put two together. Some pigments that reflect this light and some pigments that reflect this, and then it seems purple. Anyway, this is all one color, and then we move to about here, and I would say that those are like hues of the same color. Those are blues, and then about there, then it becomes a different kind of blues. And then from here to about here, those are greens. Here to here, those are yellows. This is a group of oranges. And then all of these are different colors of red, right? So I've got 1, 2, 3, 4, 5, 6, 7 different colors in there. That's it. Out of this entire continuum, there's about 7 different blocks. And I mean, I can see that there's different hues, but I would call them, it's like a slightly different red, but it's still red. Right? And that's categorical perception. We break these into categories instead of saying there's 1,000 million different individual things that I see. We don't have a color for each nanometer of light. If we did, we'd have over 300 different colors. And that's not considering like really dark ones and really light ones. The reason pink isn't on here is because it's actually, pink is red that has a lot of white in it. So it's a more diffuse version of red. Anyway, so we'd have only 300. We'd have 300 plus pure colors, and then all those with, extra white in them or extra black in them. So it would be ridiculous. Physical distance is something that we do perceive continuously, mostly continuously. It's not exactly true, but mostly physical distance is perceived not categorically, right? A longer trip feels longer. If the trip is a little bit longer, it feels a little bit longer. If the trip is really long, it feels really long. We don't break them into categories of this was a short trip, this was a medium trip, this was a long trip. We kind of perceive them more continuously. But it seems like distance is warped then in categorical perception, right? Because you can have two things that are really close together that seem, like a gorge spans them. And you can have two things that are actually quite distant but seem really close together. So one of these is, if you go back here and look at this, red spans from about 650 to at least 700, maybe 750. It's got this huge range. So if I said like 675 and 699, those look similar. There's hardly any difference between them. There's this large distance of nanometers, but perceptually, there's not really a difference. However, when you go from 600 to 650, then you cross at least 3 different colors. So a difference from, let's see, I said 675, so we're covering about 25 in there. So if we went from 625 to 650, so 650 is right here, 625 is here. If we went from 600 to 625, there's a huge amount of difference there. We go from yellow to the most reddish orange that we have on the scale. So distance is weird. It's kind of warped. Over here we travel a long distance, but it seems short. And over here we travel a short distance, but it seems long. So that's kind of odd. Boundaries are the key, though. Where there's a boundary, that kind of warps the distance and makes it seem longer. Perception then is stable over long distances when there isn't a boundary, and then when you get near a boundary, things change drastically. And you know this. We've talked about this, though, right? Because we know that all of these up here are considered E. And we can have an E that's voiced up here, and an E that's voiced down here, and it's all E. But then as soon as we kind of slip outside, so look at the distance from this corner to this corner is not really that long. It's certainly less distant than here to here. And yet, you go from one speech sound to another, but here it's the same speech sound. We could make this even crazier. We could point out that if we go from here to maybe about here, we've covered the distance of 1, 2, 3, 4 different speech sounds here to here. And yet that's still not as long as this whole thing is. So we can see that it's really the boundaries between our speech sounds that make a difference and not the actual distance in phoneme. But it's good, right? That's a good thing. It's kind of weird to think about, but it's a good thing because we can't produce our consonants and vowels the same way every time. We just can't. It's such a complex motor behavior. We're not going to hit the exact same place on our teeth every time. Not the exact same place. Sometimes we pronounce T's like T's, ta-ta-ta-ta, and sometimes they're like D's. I can't think of any sort of word right now, but sometimes we do pronounce it the. It's not exactly a the, right? It's like a the. Sometimes it comes out as duh. And so it is good that we perceive these as a the every time. So somebody who says the versus somebody who says duh, it all comes out as a the. And that's good because that way we can understand each other. Slight different placements don't really matter. And how could we ever open our mouths and have our tongue in exactly the same place? Trying to hit a mark on the teeth compared to that seems easy, and we still can't do that quite exactly the same way every time. But getting exactly the same mouth opening for E every time is almost impossible. Actually, it is impossible. I shouldn't say almost. It's impossible to get the exact placement for E right every time. Think about all the different things that can happen. Sometimes you're eating and you're saying E, but you got a mouthful of food. Of course that's going to change the way that you say the E. Maybe you're tired and your mouth isn't opening as much as usual. Sometimes people talk in the middle of a yawn. We can still understand them. The E opening has changed. And yet we still understand it as the E phoneme. If we didn't have categorical perception, this would make every single instance of the E something completely different. And we would never be able to understand anyone else, much less ourselves, most of the time. So categorical perception is great. It's a little weird to think about, but it's great. So we only really start to hear differences between them, close to the edges. Like sometimes people might say an E and it kind of sounds like an I. And maybe it sounds like they have a funny accent for a second, right? But we really only start to notice the differences then. So there's a really cool experiment that looks into categorical perception. I'm going to play one for you in a second. I couldn't find this experiment exactly, but this one looks at the differences between ba, da, and ga. If you look at the formats with ba, da, and ga, we notice that ba, just pay attention to format 2. Format 1 is the same for all of them, but ba, the format is coming up to meet the ah. With da, it's kind of staying the same. I mean, it shows it as coming down depending on your speaker. It might stay the same. It might drop just a little bit. So ba comes up, da essentially is flat, and then ga comes down quite a ways to meet the ah. So we've got a phoneme that's coming up, we've got one that's flat, we've got one that's coming down. And these are all perceived as different phonemes. Cool. You don't need to know that. I mean, you do know that, is what you don't need me to tell you that. You know this already. The whole class has been about pointing out to you that the phonemes differences, that the format differences create phoneme differences. But what we can do is we can digitally alter these so that this is definitely a ba, but we can alter the position of the format and turn it into a da or a ga. And then we can have it gradually go from one to the other. Well, what happens here is people will hear a ba here. That's not surprising because that is a ba. But right here they'll hear a ba. Right here they'll hear a ba. And then immediately, just weirdly, it switches to da. No difference in the perception. Ba, 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 da. But we know that the format has changed every time. But all of a sudden, it switches. And it's right at that boundary that we perceive a difference. Even though it's visually changing, you can see it. Okay, so the one that I have that I'm going to have you listen to is, I said I couldn't find the ba, da, ga. I could make it, and I might later and post it for you, but I wanted to get this recorded and posted, so I didn't bother making it yet. What I found is one that goes from ba to pa. So let me bring this over. There we go. So this is going to go from ba to pa. What happens is we change the voicing onset time. You're going to notice that this gets shorter and shorter. And at first, you're going to think it has absolutely no effect. And then all of a sudden, it's going to have an effect.
Ba, 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 ba,
there.
Pa, pa, pa.
For me,
as we heard, a VOT value of that a gradual delay of VOT does not
so
lead
for me, it
to
was
a
where I
differentiation
said
between
right
voiceless
there.
and voiced
It might not be the
consonants.
same for you guys.
Let us
Let's do
illustrate
it one
this.
more time.
Ba, 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 pa, 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 pa.
As we heard,
Okay.
a VOT
So-
value of around
Slightly different. Possibly for everybody. But essentially what you've got is you see that it's changing gradually, and you don't experience a gradual change. You experience a persistent ba, 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 ba. maybe right before I heard it switch over to a pa, it sounded like maybe a hiccup before a ba, but it still sounded like a pretty good ba, and then all of a sudden, pa. And then it sounded like the exact same pa every time. All right. There's some things that can push this around. I mean, the fact that we listen to it as ba to pa instead of pa to ba, that can change exactly where we decide that it switches, but it's not going to change a lot. It's going to, there might be a slight overlap, but it's not like we're going to think that it's pa all the way over here. We still maintain those categories mostly. The difference is still right at the boundary. And these are the results from that ba da ga experiment. So you can see that everyone agrees that this is a ba. And then all of a sudden, boom, it switches. And then you have about half the people saying ba, half the people saying da. And then it goes to everybody says it's a da. Da, 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 da. And then you get a fall off. This is a da to most people, but to 25% of them, it's a ga. And then we switch over, and now 75% of people hear a ga and 25 hear a da. But now we're back to 100%. So it's a really stable category when you're in it. When you're actually in it, it's very stable. When you're a little on the outside of it, it's pretty unstable, and it's a really crazy place. Well, this shows you this whole distance is constant, and then from here to here, which is about the same as from here to here, is very different. Okay, so F1 and F2, they're not the only cues, right? We have men and women and children. They've all got different format frequencies, but we still have categorical perception. So it's not just F1 and F2. There's not necessarily something special about the two of them. Because we're going to, a child has a very high voice. They're going to have higher F1s and F2s than, say, some, 8-foot tall guy, Shaq, with a super low voice has very low F1s and F2s. So it's not just the exact F1 and F2 placement. And yet we still have categorical perception, right? So we also know that when we talk faster, our formants don't change quite as much. Unstressed syllables are not accentuating formants as much as stressed syllables. They're closer to schwas when they're not stressed. And then, like I said, F1 and F2 are always moving around because of the different motor processes that we need to do to say these things. So again, F1 and F2 aren't the only thing. But we do have, it could be that there's the relative F1 and F2 difference. This should be a little bit more similar for, a 3-year-old kid and Shaq. The relative difference between F1 and F2 should be closer to the same for them. They have different size vocal tracts, but the shape of them, the way they change between phonemes should be about the same, the way they change. So then the relative differences should be something that's a little bit more stable. Another thing is, we know that, you've probably experienced this, but when somebody has an accent, even if it's an accent that it'll sound strange. You might not be able to understand them right at first. And then all of a sudden, something clicks and you're in and you understand everything they say. Now, what might be happening with this is we're using the point vowels, right? So the very edges of that IPA curve, so E and U, we're using those point vowels to construct a space, to figure out where we need to be looking for the other vowels and move our expectations of where the vowels would be to fall in line with that curve. With not that curve, but that box. Quadrilateral, I guess. This might happen sometimes. I watch a lot of British TV shows, and if I haven't watched British TV shows for a very long time, at first I'll be like, whoa, this guy is really hard to understand, but then it'll shift and I'm fine. And then if I go through a portion where I don't talk to anyone for a while, so like it's like a long weekend or maybe over summer or winter or something, and I'm watching a lot of British TV only, then I'll talk to an American person, somebody that has my own accent. And I might find it a little difficult to understand them at first too. And so what's going on there possibly is my the box of vowels is having to shift my expectations back into another region. So I have to go from British English into American English and try to figure out what's going on there. It's a little bit like normalizing or white balancing on a camera. If you're a photographer or a videographer, you know that different lighting conditions have different ambient colors, right? So this is a very yellow light that I have. But there's other, if I had a, one of those soft white bulbs that actually has more of a blue tint to it, that would make everything in here look a little bit more blue instead of yellow. So what you do to make your pictures or your movie or whatever you're shooting to look the same is you hold up a piece of white paper and you have the camera white balance onto that paper. So you take something that you know is constant and white balance onto it. And then it adjusts all the colors for what that sheet of paper looks like, and it makes everything look the same. And that might be kind of what we're doing with our point vowels. So we get point vowels, and then we kind of white balance our perceptual system to figure out where the other vowels should be in relation to those point vowels. And I mean, uncertainties are inevitable, right? We're just going to have things that people say that we don't understand sometimes. And maybe it's them saying it a little weird. Maybe it's us not paying attention exactly or expecting a different word. And then they say a word that maybe they've said just fine, but we're expecting it to be a different phoneme. And so we don't hear it correctly. That's going to happen. It's certainly going to happen. I mean, perception, perceptual differences and illusions and things like that happen all the time. Not often. I mean, 99% of the time we're perceiving things correctly, no matter where they're voiced, and that's great. But certainly there's going to be some sorts of uncertainties. It's also possible that F3, the third formant that we hardly ever talk about, and the fundamental frequency might be useful. So one thing, this is now getting into my research, the fundamental frequency changes reliably from E to well, and everything in between. High vowels tend to have a higher intrinsic frequency than the low vowels do. There's a couple different ideas about this. One older idea was that it could be tongue pull. So when you say an E, your tongue needs to come up, right? We know that the tongue is raised for E. E. So it could be that the pull of the tongue, raising the tongue, if you had 310 with me, then you'll totally know these terms. And hopefully you've had 310 from me or somebody by this point. But you say the E, and you've got the extrinsic muscles of the tongue, some of which connect down to the hyoid bone. So you say an E, and the hyoid bone is going to be pulled upwards. Now, one thing that happens when the hyoid bone is pulled upwards is that the cricothyroid joint might rock forward, and that would elongate the vocal folds, which would produce then a higher pitch, a higher fundamental frequency, in addition to creating the E. Now, what's wrong with that, though, is we can say E at various different frequencies, right? I can say E, and I can say E, and everything in between. And singers can sing them at, tons of different places. In fact, all of us can sing, not necessarily good, but all of us can sing, right? And the whole idea behind singing is being able to change your pitch at will and still be able to form all of the phonemes that you need to form. So we can go E, and it's still an E. So if the tongue pull hypothesis was true, we would expect that it is harder for us to form an E in certain places than others. Maybe it is. That's actually something I'm working on right now. Okay, this is actually kind of cool, so I'll tell you really quickly. So I have a connection to a guy named Dan Levitin. I don't know if you know Dan Levitin, but he wrote a book called This Is Your Brain on Music. He wrote the six songs. Obviously, I haven't read that book, but anyway, This Is Your Brain on Music is a book that he wrote that was really good. He's a researcher. He got his PhD from Stanford, but before that, he was a session musician and what do you call that? Not a manager. Shoot, I don't know. You know, like what Timbaland is. I can't think of what that's called, but dang. Anyway, he was that for Capitol Records or something like that, and then he went to go get his PhD. So my advisor, my former advisor, when I was in graduate school, he was my advisor. Went to graduate school with Dan Levitin, and he, from his career as a producer, that's what it is, as a producer, knows people like Sting and I mean, he's met Beyonce. There's probably no way I'm going to be able to work with her, but also Paul McCartney, right? So like huge, basically all the biggest names in music in any genre that you can think of, he knows them. So what we're trying to do is have these people who are very good singers sing their vocal range in various vowels, and we want to see if there's any reliable differences there. Don't tell anybody. This is going to be out on the internet, I know, but anyway, keep quiet until it's published. So another thing that this can be due to is a natural regularity. A natural regularity is just when two things are correlated with each other so much that we kind of perceive them almost as the same thing. So if you think of the Doppler effect, I'm sure you know about the Doppler effect. This is what makes race cars, when they pass you, sound like they go, wow, like that, or a police car. So as it's coming towards you, it has a slightly higher frequency than when it goes away from you. You should know from this class and from also 310, and maybe if you had 205 with me, that what's going on is we've got sound pressure waves. And the timing is very precise to create our perception of frequency, right? So as an object is moving towards you, it is putting out sound pressure waves at a steady rate, but it's moving. So as it's like following its own pressure wave, right? So as it follows its own pressure wave, it puts out another pressure wave. And so the pressure waves are actually closer than they should be. If it travels at a constant speed, the pressure waves are a constant amount closer than they should be. So the frequency is a constant amount higher than it should be. It doesn't get higher as it gets to you. It stays high, and then it passes you, and it drops. And now it's running away from its pressure wave. So they get a little bit further apart, which means the frequency drops a little bit. So the actual frequency would go boo, like that. Intensity, though, it's going to get louder as it gets close to you and quieter as it moves away. So it'll go ooh, like that. The Doppler effect is that boo. But then there's also something called the Doppler illusion. And the Doppler illusion is what we actually perceive when we hear something go boo, like that. An actual frequency change with the Doppler effect is about 2 semitones, but people perceive the frequency change to be 8 semitones, 4 times more than it actually is. And that's because they're conflating the change in frequency with the change in intensity. And this probably comes out of the fact that frequency and intensity are usually correlated. So if you listen to an engine revving, the engine is going to get louder as it revs. It's also going to get higher pitched. This is true for musical instruments too. If you play louder, it tends to get a little bit sharper. And this is true for our own voices. If we say hey, we whisper hey, or say, hey, really quietly. And then we go hey. And then we say hey to a friend that's, further away. And then if we say, hey, like you're shouting in anger, it gets louder, but also it increases its frequency. No matter the vowel, it increases its frequency. So that might give us evidence that the tongue pull hypothesis isn't the only thing that's at work here. So it's possible that we've learned this natural regularity and now we're just replicating it. So one way that we looked at this was we looked at scat songs, 6 different scat songs. What's cool about scat is that it's people trying to use their voices to emulate instruments. And so they're going to, our thought is that they're going to use anything that's just naturally there to kind of make their voices sound more like an instrument, to give them more range. So there's scat songs. And we also looked at just regular conversations that we took from recorded podcasts. We thought that if E's are usually produced higher than U's, we should see it here too. And then we also looked at lyrical singing. And we thought that it shouldn't be present here, because what we actually want to do is constrain our pitch to the song, to either the lyrics or the melody, and not any sort of bias that we might actually have developed. So take a really quick listen to this guy. Pay attention to the E's and the U's. That wasn't right. It's very different, right? Okay, so here's a podcast. Again, pay attention to the E's and the U's.
And the key to it is you felt you had the freedom to do it.
So this is fascinating because, of course, there's a whole body of social science research, Barry, that looks at this idea that you can actually nudge people.
Okay, so you could detect it there too, but not quite as much. And now here's a lyrical song. Pay attention to the E's and U's.
Summertime and the living is easy.
Very different. The E was the lowest thing in the song. Our results are these. This is the deviation, semitone deviation from I. So we've got E and and this is the deviation from I. So we see that 6 out of 6 of our scat songs were significantly different from one another. This is a graph. These are E's, these are U's, these are semitone differences. Very different. For regular podcasts, 4 out of 6 of them were significantly different. And overall, it was significantly different as well. The 2 that weren't significantly different on their own were going in the right direction. They just weren't quite there. And then here are lyrical songs. Only 1 out of the 6 was significantly different, but it was in the wrong direction. The E was actually lower than the and you can kind of see that here. The well, you cannot actually see that here. The error bars are just everywhere. So you can see that they're both lower than I, but which shouldn't be the case, judging from these 2. So, I. That's another thing. Go ahead and say E and I. Your tongue is pretty high for both of those. And then it's really low. So if the tongue pull hypothesis is the only thing at work here, you would expect that E and I would be very close. But actually you can see here from the error bars that E is quite a bit different than I here too. If the error bars overlapped, you would expect that they're the same, but they don't overlap, so you expect that there's a pretty significant difference there. Whether it actually is statistically significant or not, I'm not sure yet, but it is different than I. So anyway, that's the end of that lecture.